Hi, this is Rahul Makhijani here. I'm a research scientist working at Facebook. I'll be talking about our paper, Assortment Planning for Two-Sided Sequential Matching Markets. This work was done along with my co-authors, Itai, Anilesh, Daniela, and Kiran. Before I proceed, I must state that all the views expressed here are my own. The last 2 decades have seen a significant rise in the number of online matching platforms. In fact, these platforms are present in all spheres of human activity. We use apps such as Lyft and Uber for ride sharing, apps such as Tinder, Bumble, Coffee Meets Bagel for dating, apps such as Upwork and TaskRabbit for hiring workers. The nature of the platforms has also changed over time. As compared to traditional platforms where you have consumers on one side and goods on others, the platforms of today have people on both sides. This leads to interesting questions in the area of matching and market design. A key question faced by platform is to decide what subset of people should they show on one side of the platform to the people on the other side of the platform. We look at some of the trade-offs that are faced by the platform, especially in the setting of a two-step sequential platform. Over the next few minutes, I'll talk about the model we look at. We'll see that the problem, in fact, is NP hard. We propose a constant factor approximation algorithm for this problem and look at the performance of the algorithm through some simulations. So here we can, like for simplicity, we refer to agents on one side of the platform as customers and the agent on the other side is referred to as suppliers. So what does a two-step sequential model look like? So in the first step, the platform must decide what set of suppliers should they show to each customer. In this case, the platform decides to show suppliers 1 and 2 to customer 1, suppliers 3, 4, and 5 to customer 2, and suppliers 5 and 6 to customer 3. The customer has to decide or choose among one of the suppliers that are shown to them, or stay unmatched or go with their outside option. Here in this case, customer 1 selects supplier 1, customers 2 and 3 both select supplier 5. We look at the choice model or the selection model in the next few slides. Now, what happens in the second step? In the second step, the suppliers are only shown the customers that selected them. So in this case, supplier 1 would be shown customer 1 and supplier 5 would be shown customers 2 and 3. The suppliers face a similar choice to either select among one of the customers that selected them or go with their outside option. In this case, supplier 1 goes with their outside option and supplier 5 selects customer 3. We say that the match is formed if both the customer and supplier select each other. So note that each agent on the platform can make the selection only once. So what is the problem we are studying? The platform must decide what assortment set of suppliers it must show to each customer. And the goal is to maximize the expected number of matches. Now, if the platform decides to show too few suppliers to each customer, then the customer would very likely select their outside option or would end up going to a competing market. Does this mean that the platform should show all the suppliers? Now, consider a case where you have a very desirable supplier. In this case, the customers would end up selecting that particular supplier. So, for example, here, if the platform knows that, okay, the supplier is highly desirable, then both customers select that particular supplier. And in the next step, the supplier would end up selecting just one customer. In hindsight, it would have been better to show that supplier to just a single customer. So there is a trade-off between showing too few suppliers and showing too many suppliers. This is what we hope to capture in this model. Now, how does our work relate to things which have been done in the past? So the area of assortment optimization over inventory is well studied. There, the idea is to decide what subset of goods that must be shown to each customer in order to maximize the revenue. The key difference between that area of work and a problem is that goods do not have an option to reject or have no outside option. The idea of limiting choice to users is not new and has been explored in the papers by Halabert et al. And Arnosti et al. The key difference between their work and ours is we look at the two-step setting, and there the platform makes a choice over what assortment set of suppliers to show. This work has also some parallels with the literature of two-sided stable matching, where the agent choices are elicited and matching happens in a decentralized manner. In our paper, we only allow the agents to make the selection once. So what is the choice model we look at? We consider the multinomial Logit choice model. The utility of each agent is assumed to comprise of two parts, the mean intrinsic score and like a random component. Like in case of a dating market, the mean intrinsic score could be understood as a function of, say, a person's physical attributes, education, and so on. The random component is assumed to come from the Gumbel distribution. Now, the advantage of using this is the probability that an agent is selected has a closed form, which is a function of the mean intrinsic scores of the agent and the outside score that is available to that particular customer. We denote the value of a particular agent or a supplier as e raised to the mean intrinsic score of that supplier. We'll be using the term value and score interchangeably. So the probability that a customer selects a supplier J from the set that is shown to them is given by Vj divided by sum of the values of all the suppliers that are shown to them plus their outside option. So higher is the value of a agent, higher is the probability of being selected. So what are the other assumptions we look or make in our case? So we are assuming a static market setting. So we understand that this differs from reality where agents can come and leave in a dynamic manner. So there has been some work on the dynamic assortment planning, where one of the key assumptions in that piece of literature is the supplier would make and a choice immediately after the customer makes it. We assume that customers make the selection simultaneously, and in the second step, suppliers would make their selection simultaneously. So this is partially true in the case in the case of dating platforms, where like agents can make their choice at different times, like at some. The other assumption we make is we assume that the customers are homogeneous and the suppliers are ex ante heterogeneous. Now, this is again partially correct in the case where platforms have some knowledge regarding one side. So, take the case of Airbnb. There is much more information available about hosts as compared to guests, where hosts will already advertise the places much in advance. The other assumption regarding the scores and the values we make is customers have a value of 1 and the outside value of customers is 1 as well. Now, customers have values V1 to Vn over suppliers. Each supplier has an outside value of Qj. We assume that the platform knows the agent scores beforehand, and agents can make the selection only once. So now that we have gone over the model settings and the model assumptions, let's look at what is the nature of the problem. So we can show that the problem is NP hard. We do that by reducing the three partition problem to our case. As a reminder, the goal was to maximize the expected number of matches in the problem. So we've looked at various algorithms to solve this problem, and we say that the algorithm is polynomially efficient if it runs in the polynomial time in the number of customers and suppliers. We characterize the performance of the algorithm using the notion of the approximation factor. The idea is that we say that the algorithm A has an approximation factor of alpha if the expected number of matches by the menu constructed by the algorithm is at least alpha times the optimal number of matches. So we will show that we'll propose an algorithm which has a constant factor approximation. So general idea is we consider two different regimes. We consider the case of high value suppliers and low value suppliers. Suppliers are said to have a high value if their value is more than 1. One is taken is because it is the outside score of the customer. Now we also make another assumption that the outside score of all the suppliers is greater than 1. By making this assumption, we lose a factor of half. So what is the technique? So in the case of high value suppliers, we will show that there exists an algorithm which has a approximation factor of alpha h. For the low value suppliers, we'll show there exists an algorithm which has an approximation factor of alpha l. Now later on, we can combine these two regimes and show that there would exist an algorithm which has an approximation factor of at least half times the minimum of alpha h and alpha n. Now in the case of high value suppliers, we can show that it would be enough to show a supplier to a single customer. Now, intuitively, this would follow from the fact that if a supplier has a very high desirability, the customer would very likely select that particular supplier over their outside option. We also, in this case, we can also exclude suppliers which have a very high outside score, because those suppliers would very likely reject whichever customer that selects them. And in that case, you would lose a small factor. Now, considering the other remaining high value suppliers, it is easy to bound the approximation factor in this case. The interesting case is the case of low value suppliers whose value is less than 1. In this case, intuitively, these suppliers should be shown to many customers. And it's interesting to create the menu in such cases. The technique we would follow in such cases, we would find a LP relaxation for the problem. We would round the solution or the fractional solution of the LP. And based on the solution, we'll construct a menu. And we'll show that such an algorithm would achieve a constant factor approximation. So we exclusively look at the low value supplier case. So how do we construct the LP relaxation for the problem? We use the idea of bucketing. So here, like, we discretize the two dimensions. One is the supplier scores, and the other dimension is the supplier outside options. So they are discretized in the following way. All the suppliers which have like a score between 1/4 and 1/2 are assumed to have a value of 1/4, and so on. Similarly, on the outside option, all the suppliers with outside scores between 2 and 4 would have a outside score of 2, and so on. As a reminder, we have excluded the case where the supplier, we assume that the supplier's outside score is bigger than 1, and we assume that the supplier outside scores are bounded. So in this case, we have a two-dimensional bucket. So the intuition for the idea is that usually suppliers in that particular bucket are similar in nature. Using the idea of bucketing, we can show that we lose a factor of half in this case. So in general, we would have a mass of suppliers that lie in that particular bucket. So how do we construct the LP? We have an LP which has at least a factor of half as compared to the optimum value. What does the LP look like? So for each customer, we define the variable xik, which denotes that how many suppliers from bucket K are shown to that consumer. Now, the last constraint is natural for the fact that the number of suppliers that are shown to the consumer is upper bounded by the cardinality of that particular bucket. What do the other two constraints represent? The first constraint represents the how is the consumer mass distributed across various supplier buckets. So this is upper bounded by 1. The constraint number 2 indicates, like, for a given bucket, how is the supplier mass distributed across different consumers, and that is bounded again by the cardinality of the suppliers. Under these constraints, we can show that this LP would have a factor of half as compared to the optimum. Now, once we solve this LP, the next idea is to construct a rounding solution, which is to get like pick an integral number of suppliers from each bucket. Now, in the case where this value is bigger than 1, we can take the greatest integer function. Now, in the case where this value is less than 1, we add up all those masses and then distribute them roughly equally among customers. So the idea is this, that since the customers are homogeneous and the suppliers in that bucket are homogeneous, we can roughly distribute the mass of suppliers across those customers. We can show that with this particular rounding, we lose a factor of half. Once we round this, the next idea is how do we create the exact menu? Like we have decided, okay, we have the xik values, how many suppliers to pick from that bucket and show the consumer. So once we have the value of, we have the assignment, what do we do is for the xik suppliers that are shown from that bucket k, we again like create a value, like we put like a sort of score ckj for each of the suppliers in that particular bucket, and then we assign the suppliers. We use the idea which is similar to water filling. We will pick the suppliers with the lowest ckj value. So the ckj value would indicate as to how many consumers that particular supplier is shown to. In this case, for this particular algorithm, we can show that the number of consumers that particular supplier is shown to is bounded by the ratio of the outside score of that bucket divided by the value of that bucket. Now, this is like the nature of this is intuitive from the fact is that, okay, if the outside score is higher, that means you would want to show that particular supplier to many consumers, and if the value is higher, you would want to show it to fewer it's fine to show it to fewer consumers. So this is the general idea. We did a relaxation rounding and then created a menu, and then in the menu we upper bound the number of consumers each supplier is shown to, and that would give us the final approximation factor. So how well does this algorithm perform? So while the factors, like in this case, can tend to be a bit loose, we'll see that the under simulations the algorithm tends to perform well. So how do we create a simulation? We look at 100 suppliers and then we vary the number of customers. We specifically look at low value supplier case. Since for the high value suppliers, we can have a good enough value by we can see a good number of matches by showing that supplier to just one customer at a time. Now the value of suppliers is given by this fact 1 divided by 1 plus zj, where zj is our IID draws from the exponential distribution with parameter lambda v. So as you increase the parameter lambda v, in expectation the value of the suppliers decreases. The outside option is given by 1 plus wj, where again wj's are assumed to be IID exponential draws from with parameter lambda 0. For each combination of the number of customers, lambda v and lambda 0, we generate 25 instances and we look at this performance. For looking at the upper bound, we use the same LP and we compare it to this particular linear program to see how well does the algorithm perform. Now we look at the cases of the ratio of average number of matches by the algorithm divided by the upper bound, and we'll see look at the mean, minimum, and median. And we see that for various cases, for 50 consumers, 100 consumers, and or 200 customers, we'll see that the approximation factor is at least bigger than 1 by 3. Now, there are a lot of open questions from our work. So one is the current upper bound which we have is pretty loose, and it would be an interesting line of work would be to make an upper bound tighter, and then we could use similar ideas what we had to get a non-trivial approximation factor. A second problem, which a direct extension, is the case of substitution. where, like, say if a consumer is rejected, do we allow that consumer to have a second choice? And we could do study like a fixed number of rejections. Now the idea problem of substitutions is hard even in the case where suppliers have no outside option. So naturally the problem here would be much harder. And the problem can also be can there's also a natural generalization for the above problem for heterogeneous customers. So here we assume that the customers were homogeneous, and one natural question is what would be the case if customers are assumed to have like different scores and again different outside options. I will now yield the floor for questions. Thank you.